Hello everybody, today I'd like to talk about the James Webb Space Telescope and other deep space infrastructure ideas that could shake up the way that humanity travels to the distant planets, to other destinations in the future. Colonization as well as industry can be totally affected by infrastructure in an incredibly profound way. So James Webb is not only scientifically significant, but is also significant as a form of deep space infrastructure. The first, by the definition that I'll give later in this video. So first, let's talk about the science. James Webb is an incredibly important scientific instrument, potentially could shed light on astronomical issues that have been plaguing astronomers for centuries. For example, how did the first galaxies form? How did the first stars form? And did the hypothetical population 3 stars, which would have been massive and entirely composed of hydrogen and helium, did they exist? And if so, what did they look like? At least in the infrared spectrum. Along with that, we'll also be able to look at planetary systems in greater detail than ever before. And this is important because by using spectroscopy, the science of studying spectra, emission spectra, and absorption spectra of different gases and materials in the universe, we may be able to determine the atmospheric composition of exoplanets and planetary systems outside of our own. So what do I mean when I say in-space infrastructure, or particularly deep space infrastructure? And why is James Webb the first? Well, I'm going to be a little bit specific with the definition that I give here, because there are many pieces of in-space infrastructure that already exist, some of the most famous being SpaceX's Project Starlink, or something like telecommunication satellites that orbit in geosynchronous orbits around the Earth. No, but deep space infrastructure is a little bit more special. It is more difficult to get out there. So first, let me break down the difference between deep space and the near-Earth orbit regime. So contrary to popular belief, there is no sharp physical boundary between the Earth and space. In fact, the atmosphere of the Earth decreases in thickness exponentially as you go upwards. The exosphere of the Earth actually stretches up all the way to 10,000 kilometers off the surface, where it becomes so thin that it meets the solar wind, and from that point forward, the primary atmosphere in interplanetary space is the solar wind. Now, the solar wind stretches out to something called the heliopause, which is kind of the extent of the atmosphere of the solar system. And after that, the primary gaseous material is the interstellar medium, which is cold gas particles that reside between stars and float around in the galaxy. Certainly, though, the atmosphere is considered to stop and space is considered to begin at something called the Kármán line, which is about 100 kilometers off the surface of the Earth. Now, the Kármán line is where the air becomes thin enough for air-breathing propulsion like jet engines to cease functioning, and rocket propulsion to become the required method to traverse space. The air at the Kármán line is still thick enough to cause significant drag to satellites, though, and satellites, objects orbiting this low, often tend to decay in their orbits extremely quickly and come crashing back into the atmosphere. Geospace, or the near-Earth orbit regime, begins at the von Karman line and stretches out to the edge of the Earth's atmosphere, or that 10,000 kilometer boundary that I was telling you about before. Now, geospace is important because most satellites reside in geospace, and most space weather occurs in geospace. Between the edge of geospace and the orbit of the moon is cislunar space, and that area is of increasing interest to governments around the world, including our own in the United States. This region of space is considered to be an excellent proxy for deep space operations that would happen later in time, while still being relatively close to the Earth. Anything beyond the orbit of the moon is considered to be deep space by the US government. And different people have different definitions, so not necessarily everybody agrees that that's where deep space begins. But the US government thinks so. So what's the difference between a mission and infrastructure? Well, I would say that a mission serves one purpose, and there have been many space missions before, many deep space missions as well. Rovers, landers, orbiters. I would consider James Webb to be different from these things, though. The reason for that is because James Webb is theoretically open to the public. Now, the process of getting your research selected is incredibly difficult, but in theory it's possible, and therefore James Webb is available to be used by more than just one team or one person for more than just one mission. That makes it infrastructure. In the same way that a road or a bridge would hardly be infrastructural if it could only be crossed once. So James Webb is important, to say the least. By the definition I've given, it's the first piece of deep space infrastructure to exist, and that's significant. But not only that, but it also is an incredibly important instrument in and of itself. It's an infrared telescope, which is important because infrared has higher penetrative powers than optical. Because of its increased wavelength, it is able to pierce through the dust clouds that are scattered among the galaxy that absorb optical light and create these black patches when you look at them. As I mentioned before, James Webb has several scientific objectives, one of which is to view the births of the first galaxies and see how that happened. It's different from the way galaxies form today because the fact is that there are other galaxies that exist, and when they collide, when they merge, or when they interact in any sort of way, they can seed a baby galaxy and create something new that way. But that wouldn't have been possible at the beginning of the universe, before any other galaxies had formed. No, the first galaxies probably would have had to form out of the only two things that were present, which would have been hydrogen and helium. Hydrogen and helium are the only things that would have existed because those are the only things that were created after the Big Bang. Everything else in your body, the things that planets are made of, all of these things were created through supernovae processes or other chemistry that occurred later down the line. Now, to see the births of the first galaxies, we're going to need to look farther away than we ever have, and therefore peer farther back in time than we ever have. The reason that this is even possible is because light has a finite travel speed. What that means is, the farther away you look, the longer that photon has taken to travel that distance and get to your instrument. Therefore, the older it is. By doing this, we are able to peer back in time, and our telescopes become something akin to time machines. And so, along with the viewing of the first galaxies, we may also be able to see the births of the first stars. That's significant because these are the population 3 stars that I had mentioned before. They would have been composed entirely of hydrogen and helium, and they would have been massive and incredibly luminous. They're different from the stars that are born today because the stars that are born today have a high level of metallicity, including our own sun. Metallicity refers to when a star is formed with more than just hydrogen and helium, with any of the other elements in the periodic table. And this can cause smaller stars to form, more smaller stars to form, rather than fewer larger ones. By the way, astronomers call anything that's not hydrogen or helium a metal. So read it and weep, chemists. These stars may have been the first sources of light in an otherwise dark universe since the recombination event that occurred 380,000 years after the Big Bang. The light from before the recombination event was the result of the entire universe being small enough that its average temperature was equal to that of a star, and therefore all of the hydrogen, all of the helium within it was ionized and glowing. At some point, when the universe expanded enough, it cooled down to that magic temperature where all of the electrons were recaptured by their nuclei, and the universe suddenly went from being so opaque that you couldn't see your own hand in front of your face, if you could survive the searing temperature that it was at, to being completely transparent and completely dark, save for 21 centimeter wavelength light that would have been emitted by hydrogen transitioning in its superfine structure. And if you want to know more about the cosmic dark ages, I can make a video later about that. Go ahead and comment that down below. Taking a quick step back from the edge of the dark ages to the present, James Webb will also be able to observe other planetary systems like our own, and the spectral information gathered by James Webb may enable us to analyze the atmospheres of planets that are similar and dissimilar to our own. By doing so, we may be able to see the evidence of life, if it's the type of life that we have on our planet that leaves a huge impact on the atmosphere. And so the potential for science from this instrument is immense, and it's likely to rewrite the astronomy books for many years to come. So James Webb will be the first piece of deep space infrastructure. But what could come after James Webb? Well, there are a lot of zany ideas out there, including but not limited to orbital tugs, which would be spacecraft that stay in orbit and pull other spacecraft from lower orbits to higher orbits, or send other spacecraft from cislunar to deep space trajectories. Skyhooks, which would be a spinning object that has a certain angular momentum, and with the same kind of idea as an orbital tug, it'll transfer an object from a lower orbit to a higher orbit, or from a cislunar trajectory to a deep space trajectory. The difference is, rather than using chemical propulsion to do it, it'll use its own angular momentum, and then it'll have to be replenished by other spacecraft, like an orbital tug. Now, in between James Webb and the zanier spacecraft ideas that I said, which will inevitably come around at some point in the future, NASA has an idea to create a deep space gateway. This project is already in effect. It's actually part of a 3-phase plan that NASA has that's currently going on to send humans into deep space. So phase 0 is essentially what's happening right now, with experiments on board the ISS validating cislunar and deep space activities for human beings, as well as NASA's stimulation of the private space sector. They believe that by stimulating the private space sector, it will eventually grow into a flourishing market that will support human endeavors in deep space later down the line. Phase 1 consists of activities in cislunar space. This includes the validation of the Orion and the SLS spacecraft, as well as astronauts gaining increased operational familiarity with what it's like to operate in cislunar space, something that hasn't been done long-term before. And this phase will end with the demonstration of the initial capabilities of the Deep Space Gateway, which I'll get to in a bit. Phase 2 would consist of the validation, once again, the validation of Orion and the SLS, but this time as part of an integrated system called the Deep Space Transport. This system is designed to take astronauts to Mars, essentially. This phase will end when the Deep Space Transport itself is validated and proven to be Mars ready. And so now getting to what would be a pivotal part of this plan, the Deep Space Gateway. The Deep Space Gateway is essentially a relay station that could provide refuel, resupply, as well as crew lodging and extravehicular activity like repairs to spacecraft, etc., in cislunar space. This space station would orbit in a halo orbit around the Lagrange point of the Earth-Moon system that's between the Earth and the Moon. The gateway being in cislunar space would make it a much closer point of return for deep space missions, and its unique orbit would make it a candidate for science that could never be performed before. However, to fit in with the theme of this episode, the reason why I think the Deep Space Gateway is so important is because it could apply to more than just NASA. It could enable public access to space science and technology in a similar way that the ISS did so many years ago. More importantly, it can inspire the public imagination. And that is what I think is the greatest promise of the incremental, infrastructural approach that NASA is proposing here. Build a huge rocket, and yeah, you can get wherever you want. But build infrastructure. Build supply stations. Build refuel stations, telescopes, skyhooks, whatever. Enable universities. Enable developing countries. Enable small startups. Enable the public to access these things, and you're helping the rest of the world get there too. You need to build the road before you start building the cars. Thank you very much.